So in our linked list example, today we're going to target some of these missing methods, like this one, adding things into the middle of a list and deleting things from the middle of a list. Okay? Now, to do this, we have to think a little bit about the way the list exists. So I'm going to quickly draw out a diagram here of what the list might look like. Okay, so let's think about, for example, the different types of lists we could have. One of the lists we could have is this, an empty list. Okay? We could have this kind of list, a list with one node in it. Okay? Where this is null and this is null. And then we could have a list with two or more nodes. Where we're here, and then another node here. Okay, and then tail. And the connections, obviously, are going to be the important things to deal with, right? Is what are we connecting here? So this is connecting to null. These ones are connecting forwards, whereas this one's connecting to null. And obviously our head and tail are here. Okay? So when we say insert, if I say insert a spot, so if I call a method insert, I need to know a couple things. I need to know what I'm inserting. So let's say it's an array of strings. So I'm inserting, say, the word cat. But I think I need to know one other thing. I need to know where I'm inserting it. Right? We already have a method that will insert it at the head and one to insert it at the tail. So this one would be some sort of an index, like this. Insert at spot 1. So we got to think about what that means, right? If we think this is spot 0 and this is spot 1, where exactly am I inserting that node? Am I inserting it in between here? Or am I inserting it after? It's not clear. So the insert method kind of is unclear at this point as to where exactly I'm inserting it. Am I inserting it before or after? So I'm going to propose we solve that by making two methods, insert before and insert after. Okay? So in insert before, it's a little more clear. Insert before, right? So if I say insert the word cat before spot 1, now I think we have kind of a clear idea as to what's going to happen. Okay? This will be the head, this will be the tail. Okay? This will be our node going this way. This will be pointing to null. This will be our node going that way. This will be pointing to null. So what will happen is it will build a brand new node. It will put the word cat inside the node. Okay? And then it will insert it before spot 1. So if we think about the way the indexing would have worked, this would be spot 0, this would have been spot 1. So in theory, this node's going to be slipped into here. So we have to think about all the connections we have to adjust. Okay? We have to adjust several connections. Remember, right now this is the previous link. And this one is the next link. Just like this one is the next link, and this one is the previous link. But I think we can't think that this is where tail would be. It could be that that's in fact where tail is. But it could also be the case that this list keeps going for quite a long time after this. That from here, it keeps going, and tail is actually way down here somewhere. So let's think about the connections we have to adjust. In order to insert before spot 1, we need to find spot 1. Luckily, we've already got a method that can do that. We have this method called getNode, which will give us a reference to something maybe called node or current or something like that. We'll be able to get that spot 1. And then what we'll be doing is we'll be taking this thing, which will be called, let's say we call this thing node, when we create a new node, we'll be saying node.next equals, let's call that current, equals current. We'll say node.previous equals, now here's where we'll have to be a little bit strange about this. We'll have to say node.previous, that's this thing, right here, equals, and we'll have to think about a way to reference the one before, but we could say, well, current.previous. So then we could get it like that. But that won't be all we'll have to do. We'll then have to say current.previous equals node. In other words, this link will be severed. And we'll have to say current.previous, oh, but now you see we have to watch how we reference it. Maybe now we could say node.previous.next equals node. So we'll be able to do that and sever that link. So the order in which we perform that operation is really important to actually link it in properly. As well, we also have to think about the case where if we're inserting it before spot 0, that's going to be a different piece of logic because that's really inserting to the front of it. So we also have to watch that we don't go out of range. Luckily, we've built a lot of methods that are going to help do this. So let's get started. Okay, so let's write a method. I'm just going to drop mine near the bottom here. So a public void insert before method. Okay, so we're going to need two parameters. Int index, that's the spot we're inserting it before, and t data. Remember, that's the generic. So the data that we'll be inserting. Okay, well, first of all, let's use our little error check. If in range, that's when we'll do something. If it's not in range, we won't even bother trying to run any code. So that will make sure that they don't try and insert something at spot 1,000,000 when it doesn't exist. Okay, here's the easy one, the easy thing. If the index equals 0, think about what we're doing here. We are inserting before spot 0. What can we use something we already have to do that? Yep. We can call insert head, because that's what we do, right? We're inserting it at the head if it's at spot 0. Because that just means we're inserting it before the very first spot anyway. So we already can do that. We'll just send the data over to insert head, and it'll take care of all that code for us. Now we come down to the else statement. Okay, so here's what we have to do. First, let's build a node. Node equals a new node, and we'll put the data into it. So now we have a blank node built. Okay, it's not connected into the list yet. Now we need to find the spot in the list that we're going to connect to. So we'll make a node called current equal to getNode for the index. So that's where, again, that little method comes in handy. We'll find that spot. Remember, current isn't building a brand new node. It's just a reference to a node that's already in the list. Now, I'm just going to leave a blank line. We are going to do this. We are going to increase the length. We can't forget about doing that. That has to happen. But now we need to make those connection lines that I was talking about. Okay? So here's what we have. We have a list with a node that we found right here called current. So current is connected at this point. We also have built a brand new node called node right here. So that's what we have. We have a reference to this spot, and we have a reference to our brand new node. We now need to make those 4 connections work properly. So I'll give you, and the order matters. So here's the first line. We'll say node.previous equals current.previous. Okay, so let me explain what that just did. This is node right here. We said node.previous, that's this thing, is equal to current, which is this thing, dot previous. So what current.previous points to is this node. So we just made that connection right there. That was a good one. That was supposed to happen. So that's our first connection made. The next line will be current dot previous. Oops, too many R's. Now here we're going to do a double reference. Dot next equals node. Okay, get rid of this line right there. Okay, so here's what this line did. When I said current, talking about this thing, dot previous, that's that thing, but then I double reference it. So I said current dot previous dot next. I'm talking about this line right here. I'm now severing that line, and instead I'm pointing this thing to the node. So I've kind of just chained that into here right now. Now what that would mean is that the rest of this list is right now technically cut off, except I still have a reference hanging on to it. I still have current. So let's go to the next line. So now I'll say current dot previous equals node. So what that line did is it went to here and it said current dot previous. That's this link now I'm going to sever. And I said now you are connected to the node. I only got one thing left to deal with, and that's node itself. So now I say node dot next equals current. And that should do it. So now node dot next, that's this link right here, is equal to current. And as you can see, it has now inserted that node before the current node. Now when this method is done, current will no longer exist as a reference. But that's okay because the rest of our list will have it connected. Node will no longer exist as a reference, but the memory will exist within the list. All the list references that are left are head and tail, wherever those happen to be. So that's the logic for doing that, for inserting before a node. Let's see if it works. Let's add a line to our main. I'm just going to run main once just to see what our list looks like at this point, because I kind of forgot what it looks like at this point in our testing. We were testing delete head, we were testing delete tail, we were testing quite a bit of stuff. So I'm just going to run it just to see what our list looks like at this point. And I guess I should have run this before class. Always that first run takes a while. Okay, so right now our list just has a 5 and a 55 in it. So I'm going to try and call insert before spot 1, because there is a spot 1, right? There's a 0 and a 1. So I'm going to try and insert something before 55. So I'm going to call it, I'm going to say list dot insert before, and I have to give it a number. So I'll just give it the number 50, and I'll put it before, or actually, sorry, I put that in the wrong order. The first parameter is the spot, and then I'll spit out the list. So I'm going to try and insert a 50 before spot 1. Let's see what happens. Look at that, it worked. The 50 is now before spot 1. I'm going to do one more quick test on it. I'm going to say list.insert before, but this time I'm going to try and insert before spot 0. That should theoretically put it at the very front of the list, and I'll just put a 3 there. And let's see, and then I'll do another output of the list. I'll run it, and sure enough, the 3 was put at the front. So insert before works fine. So by adding these 4 lines of code, I was able to kind of test that. Now I could also run a test to see if insert before uses the out of range method, but I think we'll go with that. It's going to work. Okay, so that's insert before. Now let's write insert after. Public void. And you know what? It's so very similar. I'm just going to steal all the code from insert before and just make the changes. So I'm just going to rename it insert after. And we'll just make some changes. So what's wrong with this line in insert after? Right, it shouldn't be insert head, it should be insert tail. That's right. But is this the right value to look for? No, I wouldn't insert tail at spot 0. I would insert tail at spot length -1. That's the last node in the list. So in other words, I'm saying if I'm trying to insert at the last node, then just go ahead and call insert tail. So that's equal to length -1. That's the spot at the end of the list where we'll insert after. These two lines will be the same. Node will be created. I will create a reference to the current node. But then after that, these 4 lines will all change. This line will stay the same. But these 4 lines are going to be different. So I'm just going to put some space there right now just so you guys can see it easier on the projector. Okay, the first line. Okay, it will be node dot, not previous, but next. And it won't be current dot previous, it'll be current dot next. Basically, these are all going to flip-flop, okay? Then it will be current dot next dot previous equals node. And then it will be current dot next equals node. And then the final line will be current node dot previous equals current. So basically, these 4 lines, you flip all your nexts and previouses around. And then it should be okay. The logic should stand that if we flip those around, it should be doing the reverse. Now, I could draw that all out for you guys, but I think you could probably just take my word for it that that's going to work. But let's run a test on that and just see, okay? So let's test that in our little main method as well. Okay, so now we'll do list dot insert after spot 1. I'll put a 12. And then I got to remember to output the list just to see if it worked. So let's see what happens. Okay, so this was the list right here, and I said insert a 12 after spot 1. So here was the list, and then sure enough, there's spot 1. Look at that, a 12 was inserted after it. So that worked well. And let's just try it with the end of the list. So at this point, I forgot to count. I'll have 0, 1, 2, 3, 4. I'll have 4 nodes. So I'll try to do a list dot insert after spot 4, and I'll put the number 256. Let's just see. Uh-oh. Oh, I forgot to output it. Crucial error. So there's 256, and then I'll output the list. And sure enough, there's 256 sitting right at the end. So this is now very, very powerful in terms of the stuff you can do with this linked list. Now we can add things in the middle of the list as well, but not just the middle, but in the middle on either side. Way more powerful than an array in the sense that you can add stuff kind of everywhere within the list itself. Now let's focus on the delete. How can I delete something from the middle of a list? Now for this one, for delete, if we look at our diagram, let me just jump to this one. We can already delete from the front of a list. We can already delete from the back of a list. What I'm asking to do right now is delete something in the middle of a list. Okay? So here's what we could have. If I say delete, I need to know where, right? So I could say, for example, delete spot 1. So if we think about the indexing, that would mean that this spot right here, spot 1, will be deleted. We already have an in-range function, so we'll make sure it doesn't accidentally try to delete something outside the range. That will be easy. But what delete will actually do is it will take this link here and redirect it around the node that we're trying to delete. It'll take this link here and delete it around the node that we're trying to delete. So it has 2 references to redirect, and then it will sever this thing, and it will sever this thing. Therefore, this node right here will be considered a deletable node. It no longer is referenced. But we need to find that node. We need to make a reference to current and then the way we reference it will be important. So let's get started. And I think we can do this before the end of the period. I have confidence that we can. All right, so let's add this method to our giant, robust linked list class. It will be a public. No, it won't be a void method. We're going to make this return the data. So we'll make this a T method. So instead of just doing nothing, it will return the actual value. Delete int index. Okay, first thing is we'll check to see if it's in range. That's easy. Because if it's not in range, we'll just return null. So we'll return a null value if it's not in range. Simple enough. Okay, there's a couple easy ones we can deal with first. If the index, we saw this in the last one, equals 0, you know what I'll do? I'll just return delete head. Because that does the same thing. So if it's at spot 0, I'll just wipe out the head and return that value. Otherwise, else if index equals length minus 1, I'll just return delete tail. Same thing. That's easy. Those are the two spots on the two ends, delete head or delete tail. So those are easy. Those are easy to deal with. At spot 0 or spot length minus 1, I can just do those two things. But then the else statement here that we're about to write is for anything actually in the middle. Okay, so first thing, we're going to make a node called current equal to get node. So we get the spot that we're looking for. Okay, here comes the referencing. And again, it uses a lot of double referencing. Current dot previous dot next equals current dot next. Okay, so I want to kind of draw this a little bit as I'm writing these lines. So we're in the middle of a list, so I'm going to draw at least 3 nodes here. Okay, we right now have a reference to current. This is the one we're going to delete. Okay, so this first line says current, that's this thing, dot previous, that's this thing, dot next, that's this thing. So I'm talking about this reference. I'm moving it to current dot next, which is this thing. So I just made that redirect. Okay? So the only way I can do that is with that kind of fancy double referencing there. So that goes around the node that we were trying to delete. Next line will be similar. Current dot next dot previous equals current dot previous. Okay, so let's think about what that reference means. So I say current, that's this guy, dot next, that's this guy, dot previous is this thing, that reference there, equals current dot previous. So that just made that link go around to here. So that's what I just did to make those connections happen properly. I severed that link, and I severed that link, and redirected them around the node I'm deleting. Okay, that was pretty easy. Let's go to the next line. Current.next equals null. And then current.previous equals null. There's the next 2 lines. All that does is it takes current and severs that link to null, and it severs that link to null. Now look at where current sits. It's just floating outside the list. It has been cut away. The final line is just length. Actually, sorry, there's one last line. Length minus minus. That reduces the count. And then finally, we return current.data. But we have to do one other little thing to it. You may recall Let me just clear this diagram off. We have to cast it as type T as our template. So that'll allow us to delete nodes, theoretically, from the middle of the list. Okay? These were, by the way, these last couple methods we just wrote here were the longest methods we've written so far. They weren't that bad, but you had to really understand the referencing going on. So let's test this delete before we wrap up for today. Let me just run it just to see what the list looks like. Okay, so that's what it looks like. So I'm going to try and delete this spot in the middle. That's spot 0, 1, 2, 3. I'm going to try and delete spot 3. So list.delete spot 3. And then I'll print the list. Whoops. Come on. Oh, everything's going crazy. My computer's going slow and crazy. What's going on? There we go. Okay. Try and delete that 50. And sure enough, look at that. The 50's gone. I'm going to try and delete spot 0 as well, just to see if it makes sure that that works. List.delete spot 0. Print out the list. And yep, spot 0, 0, 1, 2, 0, 1, 2, 3. Let me just try and delete spot 3, which should delete the last one in the list. And yep. So you can see here, I can make my list grow and shrink dynamically in all different spots. I can add in different spots. I can delete in different spots. I have a really powerful class now. If you just look at what our list can do, just based on the methods that we've been building, all these different delete and destroy and get and set and is it empty and give me the length and insert, way more powerful than an array at this point. And it can store anything, not just a specific data type. So that's where we're going to stop for today.